Welcome back to Physics 192. I'm Gerard Blanchard. This time, we're going to continue our discussion of radioactive decay with beta plus decay and electron capture. A beta plus particle is a positron, or in other words, an anti-electron. An example of a beta plus decay would be nitrogen-13 decays into carbon-13 plus a positron plus a neutrino. Now, nitrogen is element 7, so it has 7 protons, and carbon has 6 protons, so we have 7 protons on the left-hand side of the reaction. We have 6 protons plus a positron on the right-hand side of the reaction, so we have conserved charge. We have 7 plus on one side and 7 plus on the other side. We've also conserved nucleons because nitrogen-13 has 17 nucleons, 7 protons and 7 neutrons, whereas carbon-13 also has 13 nucleons, 6 protons and 7 neutrons. So what's happened here is that a proton has changed into a neutron plus a positron. That's the effect of the weak nuclear force. Now, if beta plus decay can occur, then electron capture can also occur. What happens in electron capture is that a proton in the nucleus captures an orbital electron and becomes a neutron plus a neutrino. An example of this would be nitrogen-13 captures an electron and becomes carbon-13 plus a neutrino. Once again, we've conserved charge, we've conserved nucleon number, and we've also conserved electron number because the electron balances out the neutrino. And also, in beta plus decay, the positron and the neutrino balance each other out in terms of electron number. Now, the reason why electron capture can always occur whenever beta plus can occur is that we have more energy on the reactant side of electron capture. We have an electron on the reactant side in electron capture and less energy on the reaction side. We basically move the mass of the positron or electron from the product side to the reactant side. So if beta plus decay can occur, then electron capture can always occur, but the converse might not be true. There might not be enough energy released for beta plus decay to occur in some situations where electron capture does. Let's work an example. Write out the reaction and identify the daughter nuclide when sodium-22 decays by electron capture. From a table of the isotopes, the atomic number of sodium is 11. The mass of a sodium-22 atom is 21.9944 atomic mass units. Neon is element 10, and neon-22 has a mass of 21.9914 atomic mass units. Magnesium is element 12, and magnesium-22 has an atomic mass of 21.9996 atomic mass units. So please answer the question. So we have sodium-22, and I'll just note that we have 11 protons and 11 neutrons, and it captures an electron. So now we will have, what we have is a proton turning into a neutron. So we will have 10 protons and 12 neutrons. And so that would be element 10, which is neon. So we'll have neon 22, and then we have to have a neutrino to balance out our electron number. So we have conservation of nucleon numbers. We have 22 protons and neutrons. We have conservation of charge. We have 11 plus for the 11 protons minus 1 gives us a total charge of 10 over here. And we have 10 protons, so we have a total charge of 10 over here. And we've balanced out our electron number. We have an electron being balanced by a neutrino. Okay, let's figure out the energy now. The atomic mass of a sodium-22 atom, so we have, is 21.9944 atomic mass units. 9944 atomic mass units. Now from that, I have to subtract off the mass of 11 times the mass of an electron. But now I have to add in the mass of this electron. And then over here, I have the atomic mass of neon, which is 21.9914 atomic mass units. Now from that, I have to subtract off the mass of 10 electrons, so minus 10 times the mass of the electron. And then the mass of the neutrino is effectively 0. It's negligible. So what you can see here is that I have to subtract off the mass of 10 electrons here and subtract off the mass of 10 electrons here. That's so we can get our nuclear mass. These numbers right here that are given in the table of the isotopes are the mass of the sodium atom and the neon atom. So we have to subtract off the mass of the electrons that are in the atom if we want to get the mass of the nucleus. But since we are going to subtract the mass on this side from the mass on this side, we can in fact neglect the mass of the electrons because we're subtracting off 10 here and subtracting off the mass of 10 electrons here. So that's not going to make any difference when we subtract one side from the other. So I'm going to cancel out the mass of these electrons and not worry about it. Okay, so on this side, we have 21.9944 atomic mass units, which now we have to multiply by c squared. And c squared is 931.494 mega electron volts per atomic mass unit. And that goes to 21.9914 atomic mass units times 931.494 mega electron volts per atomic mass unit. And what are those energies? We have 21.9944 times 931.494. And so we have 20,487.7 mega electron volts on this side, and that goes into 21.9914 times 931.494. that goes into 20,484.9 mega electron volts on this side. And so the difference, the excess, the energy that is released when we go from here to here, is going to be a difference of 7.7. Everything is the same. 7.7 minus 4.9, which is going to be 2.8 electron volts. So the change in energy is 20,487.7 MeV minus 20,484.9 mega electron volts, and that is, as I said, 2.8 mega electron volts. So when this sodium nucleus captures this electron and creates a neon, it also releases 2.8 mega electron volts of energy. Now once again, notice that I could cancel out the mass of the electrons because I wound up subtracting this side from this side. So the mass of the electrons didn't matter in the end. So far we've talked about alpha decay, beta decay. Let's talk about gamma decay. A gamma ray is a photon. Neutrons and protons in nuclei have discrete energy levels similar to the electron energy levels in atoms. And if a nucleus is in an excited state, then it can transition to a lower state by emitting a gamma ray. Let's take a look at this diagram. All the way to the left, you see a nitrogen-12 atom. You see the energy states in a nitrogen-12 atom. The protons are on the left and the neutrons are on the right. So they all have energy levels. The proton energy levels are spaced out a little bit more than the neutrons are because the protons repel each other, so they get a little bit higher energy levels than the neutrons. And as we go up the page, we are going in the direction of increasing energy. Now these energy levels can each be occupied by 2 protons, just like every electron energy state can be occupied by 2 electrons. So nitrogen-12 has 7 protons and 5 neutrons. If the nitrogen-12 undergoes beta decay, then 2 distinct things can happen. 98% of the time, the nitrogen-12 decays into carbon-12, and the proton goes right into the open space in the neutron, and the proton that becomes a neutron goes right into the empty space in the neutron energy levels. So all of the energy is released at once. That is the diagram at the upper right-hand side. And that happens 98% of the time. 2% of the time, however, when the nitrogen-12 undergoes beta decay, the proton doesn't go all the way to the lowest available energy state. It goes to a higher state, which puts the carbon-12 nucleus in an excited state. Just as you learned in chemistry that atoms can be in an excited state when their electrons are in a higher energy level than the ground state. So there you see that the proton turned into a neutron, but now it's in an excited state. It released a little bit of energy because the proton was at a higher energy level than it wound up in, but there is a lower energy state for the now neutron to fall into. And when the neutron falls into the lower energy state, it releases a gamma ray. specifically a 4.4 mega electron volt gamma ray. So the carbon-12 in its excited state becomes carbon-12 in its ground state. So that is what happens when gamma decay occurs. It is a transition from an excited nuclear state to a lower nuclear energy state. The final radioactive decay process that we saw in our chart of the isotopes was spontaneous fission. Spontaneous fission means that sometimes nuclei just fall apart on their own. And these are large nuclei, so it is large nuclei that can spontaneously fall apart on their own. And this is called spontaneous fission. Fission means to cut apart, so they will spontaneously break apart. As an example, californium-252 can fission into iodine-137 plus rhenium-112 plus 3 neutrons. So the question is, how much energy is released when californium-252 fissions spontaneously into iodine-137 plus rhenium-112 plus 3 neutrons? From a table of the isotopes, californium-252, which is element 98, has an atomic mass of 252.0816 atomic mass units. Iodine-137 has an atomic number of 53 and an atomic mass of 136.9179 atomic mass units. And rhenium-112 has an atomic number of 45 and an atomic mass of 111.9144 atomic mass units. So how much energy is released when this spontaneous fission process occurs? Here's our reaction. Californium-252. And I'll make a note here that it has 98 protons. It falls apart and it turns into iodine-137, which I'll note has 53 protons. And rhenium-112, which I will note has 45 protons, plus 3 neutrons. Now let's check. 98 protons becomes 53 plus 45 protons, so that's 98 protons, so we conserve charge across the reaction. How about nucleons? 137 nucleons plus 112 nucleons is 249 nucleons, plus 3 more nucleons gives us 252 nucleons, so we've conserved nucleon number. So this is an allowed reaction, at least as far as those two rules go. Let's check the energy. On this side, we have 252.0816 atomic mass units. And then I will note that we have to subtract off 98 times the mass of an electron. And that goes into iodine-137, which is 136.9179 atomic mass units minus 53 times the mass of an electron. Rhenium-112 gives us 111.9144 atomic mass units minus 45 times the mass of an electron, which would be plus, and then plus 3 times the mass of a neutron. So it'd be 3 times 1.0087 atomic mass units. And once again, notice that we're subtracting 98 electron masses from this side, and we're subtracting 98 electron masses from this side. So when we compare the two sides, when we subtract this side from this side, those will cancel out. So I'm going to go ahead and cancel out those electron masses now. And this time I'm going to do things slightly differently. This time I'm going to add up all of these atomic mass units first, so we don't have to multiply so many different things by c squared. So on this side we have 252.0816 atomic mass units turning into, let's see, 136.9179 plus 111.9144 plus 3 times 1.0087 atomic mass units. And that gives us 251.8584 atomic mass units. So this many atomic mass units turns into that many atomic mass units. And what I'm going to do is I'm just going to subtract these masses from one another. So we have 252.0816 atomic mass units minus 251.8584 atomic mass units gives us a difference of 252.0816 minus 251.8584 atomic mass units. That gives us a difference of 0.2232 atomic mass units. So we have a decrease in mass of 0.2232 atomic mass units. Now I'm going to multiply this decrease by c squared to get the energy released. It's mathematically the same as we've always done before, just it's a little bit less computation. So that's why I'm showing you this way as well. But mathematically, it's exactly the same. So now we have 0.2232 atomic mass units times c squared, mass times c squared, and c squared is 931.494 mega electron volts per atomic mass unit, and that gives us 0.2232 atomic mass units times 931.494 mega electron volts per atomic mass unit gives us an energy release, gives us a big energy release of 207.9 mega electron volts. So you can see that a lot of energy is released when this californium breaks up into these different component atoms, these product atoms. Now that we've learned about radioactive decay, let's talk about radioactivity. The important thing to know about radioactivity is that nuclear decay, whether it's alpha decay, beta decay, gamma decay, or spontaneous fission, nuclear decay occurs randomly. So all we can talk about is the probability that a single atom will decay at any time. That gives us the decay constant, which is represented by a lowercase lambda, lowercase Greek lambda. And the decay constant lambda is the probability that any single atom will decay in any 1 second period. Therefore, the radioactivity capital R, is equal to the number of atoms that you have present in a sample times the decay constant. Or R is equal to N times lambda. Now what this means is out of a group of N atoms, R will decay and radiate each second. Radioactivity is measured in units of becquerels, or the number of decays per second. Every second, some of your atoms in your sample are decaying. Therefore, N decreases over time when the atoms decay. That means that the radioactivity also decreases over time. The radioactivity follows the law. Radioactivity is equal to radioactivity 0, or the radioactivity that you had initially, times 1/2 raised to the power of T divided by T 1/2. So from the decay constant, which is the number of decays per second, we get the half-life by taking the natural log of 2 and dividing it by the decay constant. That turns that into a time, or a number of seconds, and that is the half-life of whatever particular radioactive material you have. And the radioactivity over time goes as radioactivity is equal to radioactivity 0 times 1/2 raised to the power of T divided by the number of half-lives. Let's work an example so that you can see that equation in action. A certain radioactive nuclide has a half-life of 200 seconds. A sample containing just this one radioactive nuclide has an initial activity of 80,000 becquerels. How many nuclei were present initially? What will the activity be 600 seconds later? So please work on that question. We can answer the second question first. Radioactivity is equal to radioactivity 0 times 1/2 raised to the power of T over T 1/2. Or radioactivity is equal to radioactivity 0, that was 80,000 becquerels, times 1/2 to the power of 600 seconds, that was T, divided by the half-life of 200 seconds. So you can see here we have the same units. Our seconds cancel each other out. So the radioactivity is 80,000 becquerels times 1/2, and 600 divided by 200 is 3. So 1/2 to the third power. So you can calculate that. Radioactivity is 8T1000 times 1/2 raised to the third power, which gives us 10,000 becquerels. So, if a radioactive sample has an initial radioactivity of 80,000 becquerels and the half-life of that radioisotope is 200 seconds, or a little over 3 minutes, then 600 seconds later, or 10 minutes later, the radioactivity will be down to 10,000 becquerels. So that was the first question we were asked. The second question is, how many nuclei were present initially? Well, we know that radioactivity is equal to the number of atoms present times the decay constant. So the initial radioactivity would be equal to the initial number of atoms present times the decay constant. So the initial radioactivity divided by the decay constant is equal to the number of atoms initially present. So we have to figure out the decay constant. Well, we know that the half-life is equal to the natural log of 2 divided by the decay constant. So the decay constant will be equal to the natural log of 2 divided by the half-life. So the decay constant is the natural log of 2 divided by 600 seconds. And what is that? Natural log of 2. Okay, let's see. Hang on 1 second. I gotta find the right button. Okay. The natural log of 2 divided by 600 seconds gives us a decay constant of 1.16 times 10 to the minus 3. Decays per second, so inverse seconds. So that tells us that the probability that an atom will decay in 1 second is 1.16 times 10 to the minus 3, which is about 0.1%. So each atom has a probability of 0.1% of decaying every second. That's what the decay constant tells us. Okay, so radioactivity 0 of 80,000 becquerels divided by a decay constant of 1.16 times 10 to the minus 3 decays per second is equal to the number of atoms initially present. And so that would be 80,000 divided by 1.16 times 10 to the minus 3. And that is 1, 2, 3, 4, 5. That is 69 million. That would be 69.0 times 10 to the 6 atoms is equal to N0. So initially, there were 69 million atoms present, but they decayed over time into something else. So far, we've been talking about how atoms decay or fall apart. How are they created in the first place? Bringing together light nuclei can also release energy. This is called fusion. For example, if you bring 2 hydrogen-2 nuclei together to create a helium-4 nucleus, we can go through the math. You would have 2 times 2.0136 atomic mass units for each hydrogen-2 nucleus, and that goes into 4.0026 atomic mass units, which is the mass of a helium atom. So from that, we have to subtract off twice the mass of an electron, or minus 2 times 0.00549 atomic mass units. So we have 4.0272 atomic mass units becoming 4.0015 atomic mass units. So as we bring those two hydrogen-2 nuclei together to form a helium-4 nucleus, they lose mass or release energy. We can calculate the energy released, 4.0272 atomic mass units times c squared, which is 9.31494 mega electron volts per atomic mass unit, yields 4.0015 atomic mass units times c squared, which is 931.494 mega electron volts per atomic mass unit. So we have 3.751.3 mega electron volts becoming 3.727.4 mega electron volts, or releasing, what is that, 23.9 mega electron volts as those hydrogen-2 nuclei come together to form helium-4. So when they get together, they release energy. However, it is very hard to bring together two hydrogen-2 nuclei because of the electric repulsion between the protons. Once we get them close enough together that the strong nuclear force can take over, we will release energy, but they have to have a lot of kinetic energy or a high speed to begin with just to get that close. So, let me ask a question. How fast must a hydrogen-2 nucleus be moving to approach within 3 × 10 to the minus 15 meters of a stationary hydrogen-2 nucleus? I'm going to work that out for you. That is an energy question. So here I have a hydrogen-2 approaching a stationary hydrogen-2. So 2H. So this is our initial condition. And initially I'll say that this is infinitely far away from this one. Finally, I'll say that they're separated by only 3 × 10 to the minus 15 meters. So we go from a hydrogen nucleus being very far away with some V initial to being at rest. We'll say V final is equal to 0. So R initial is infinity, V initial we don't know. R final is 3 × 10 to the minus 15 meters, but V final is 0, so they've gotten close enough. So this has gotten close enough that the strong nuclear force can take over. But it's going to have to be moving very fast. Okay, how do we work that? That's an energy situation. We have work non-conservative is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. The only forces acting on this particle as it approaches is the electric force. So the work non-conservative is 0 because the electric force is a conservative force. So 0. Final kinetic energy is 0 because it's at rest finally. Initial potential energy is 0 because the proton is initially infinitely far away. So that's 0. So we're left with 0 is equal to minus kinetic energy initial plus potential energy final. That tells us that kinetic energy initial is equal to potential energy final, or 1/2 mV initial squared is equal to is equal to K times Q1, Q2 over R, or 1/2 the mass of the hydrogen 2 times V initial squared is equal to K, and that'd be R final, times the elementary charge squared divided by R final. We can solve this for V initial. So V initial would be 2K E squared over M R final, and then take the square root. Okay, now we need to get some numbers into here. V initial is equal to 2K is 8.988 times 10 to the 9. The elementary charge is 1.6 times 10 to the minus 19 squared. We need the mass of a deuterium nucleus, and that is going to be about, I don't have to be exact here, about twice the mass of a proton, or 2 times 1.67 times 10 to the minus 27 kilograms times radius final, which is 3 times 10 to the minus 15, and take the square root of all of that. And so what is that? Okay. Take the square root of 2 times 8.988 times 10 to the 9 times 1.6 times 10 to the minus 19, and we'll have to square that. And then we have to divide by 2 times 1.67 times 10 to the minus 27 times 3 times 10 to the minus 15, and that all works out to 6.78 times 10 to the, let's see, 1, 2, 3, 4, 5, 6 times 10 to the 6 meters per second. So this deuterium nucleus, or this hydrogen-2 nucleus, has to be moving at 6.78 times 10 to the 6 meters per second in order to get close enough to the other deuterium nucleus in order for the strong nuclear force to take over, so that those two nuclei will fuse into helium-4. So, nucleosynthesis by fusion occurs where there are high-speed nuclei present. Where would that be? Well, that happens in the Big Bang. That happens in stars, supernovae. That even happens here on Earth inside of particle accelerators. What about neutrons? A neutron wouldn't be repelled by the protons in the target nucleus. Free neutrons can approach a nucleus without electric repulsion and fuse, but unfortunately, free neutrons are very short-lived. A free neutron has a half-life of only 10 minutes. So nucleosynthesis by fusion with neutrons only happens where there are a lot of neutrons being produced very close to your target nuclei. So this is the end of Physics 192, the end of general physics. In Physics 191 and Physics 192, we've covered everything from systems as large as the moon orbiting the Earth, all the way down to subatomic particles. We've covered gravity, we've covered electricity, we've covered the strong and the weak nuclear force. We've covered things in between, such as elevators and balls and cars. So physics is happening all around you. Your general physics can help you understand things going on all around. So I hope that every day you think physics.